Hi everyone, welcome back to my new video on AVL trees. My name is Alex and today I'm excited to walk you through my advanced AVL tree projects which I created for my data structures course on AVL trees. Before I get into this advanced variants, I want to quickly explain why AVL trees are so important in computer science. So AVL trees are one of the earliest and most widely used self-balancing binary search trees. After every insert or delete, the tree auto rebalances using rotations, and this makes sure that there is fast and predictable performance, that order log n has search, insert, and delete, and it's perfect for systems requiring guaranteed time complexity. So AVL trees show up in real systems like indexing engines, compilers, memory allocators, file systems, metadata, and algorithm libraries. So understanding these trees is a foundation for understanding almost any high performance data structures. So yeah, let's get into it. So for the first part of this, I will be showing you guys how just the standard AVL tree demo for now. Just let this load up for a second. Okay. So let me just get this camera out the way. Okay, so yeah, here is my interactive menu. So as you can see from the last video, if you want to just look at the main stuff I went over, I went in depth on like the insert, delete, search for, and then to display like just the basic AVL tree. So I could go over that right now for you guys, just so you guys could get a little, just so you guys could see how that works. So yeah, so let's go ahead and select option 1. So we have to put in a key. So let's put a key 50 and then a value of V50. So it takes us right back to this menu. So let's say we want to display this structure. So let's click 5 and it displays that structure like this. Let's say we want to delete that. Let's delete that key 50 and let's make sure that that deleted. So let's go back to the display. And yeah, so as you can see, nothing's displayed now. So that's just like the simple AVL tree, but we could also go more in depth. So let's go insert multiple values. So let's do 50, V50, 30, V30, 70, value 70, 20, 40, value 40. Let's get a couple more of these. Let's get one more, 80, value 80. So putting these values in will trigger rotations automatically to keep the tree balanced. And as you can see, all of them are being displayed right here. They're going side by side right now. I could make this a lot cleaner as I get more into, as I do more into my project, which I would like to display this one after another, which will be easy to do. I'll just have to put an end line after every print statement. So now let's go into my advanced AVL variants. So let's move to this part of my project. I implemented 4 advanced AVL tree variants, which are very important to know. So as you could see in my last video, I didn't have this option 7. It goes into advanced AVL variants. So let's click that option and see what we have here. So we have threaded AVL trees, persistent AVL trees, AVL and hash hybrid trees, cache-friendly AVL trees, and an option to go back to the menu. So I'll go over each of these and explain what they do. Yeah, so let's start with Threaded AVL Trees. So let's click that option, and it gives me another clean submenu right here with functionality of inserting, delete, search, pre-order traversal, in-order traversal, post-order, and level order, and display the structure. So let's give a little bit of background of what a threaded AVL tree is. So a threaded AVL tree replaces null pointers with threads and pointers to the in-order predecessor or successor. So this improves traversal speed and eliminates the need for recursion of stacks. You may ask why it's advanced. It makes sure that there's in-order traversal becomes extremely fast, requires careful thread maintenance during rotations, and it's great for memory constrained or interrupt safe systems. So some examples when this is used is in embedded systems or real-time systems where recursion is expensive or where there's low memory hardware applications. So let's go through this. Yeah, so let's choose the option 1 and insert these some values, and we'll show you guys how the traversal actually works. So let's do key value 30. Let's do a couple more here. And one more. Okay, so now let's go to the threaded in order traversal to see what happens. Okay, yeah, so I got it to work. So as you can see, there is the pre-order traversal right here. So that is the traversal one. So now let's go back to the main menu. I'm sorry, back to advanced AVLs, and let's go into persistent AVL trees. So you may ask what a persistent AVL tree is. So persistent AVL trees store every historical version of the tree. So every insert or delete creates a brand new version using path copying while sharing unchanged subtrees. So why it's advanced, it enables time travel queries, never overwrites old data, and this is super important. And it is used heavily in functional languages and versioned databases. And some use cases of this would be like Git-like version control systems, undo/redo engines, and things like that, basically with version control. So let me show you guys how this works really quick. So let's go to the fourth option. The first option, which is to insert. So let's insert a key 10 with the value of v10, and then let's insert a couple here. So let's do another one, maybe 20, 20, and 30, 30. So now let's see this displayed. And it, as you can see, it asks you for a version. So let's say version 1. So if you remember, our first version was the 10. So now let's do that again and see if the other ones will display to make sure that I got this code correct. So let's go into back into that display feature, and let's do 3 this time. And shows you this right here. And then let's do one more. Version, I'm sorry, I think I clicked the wrong one there. Let's try that one more time. So display it 3. So it now displays all of them, you see. And let's say we wanted to just display the first 2. Let's go version 2, and you can see it's only these. So that's pretty cool. It shows every single version based on how we did it, and each version is fully preserved and nothing is lost. So now let's go back into our other submenu, and let's go with the AVL hash hybrid trees. So let's click that option, And let me tell you guys a little bit about hybrid AVL trees. So this structure combines AVL tree for sorted order and hash table for order 1 exact key lookups. And every insertion updates both structures actually. So why is this advanced? So it provides the best of both worlds. So there's fast searched, there's ordered traversal, there's balanced structure, and it's frequently used in high performance databases, caches, and indexing engines. So examples where this is used is in database query indexing, memory indexing structures, ordered maps with constant time searches, and runtime symbols tables in compilers. So let me start with the demo for this one. So let's choose option 1 here, and let's add some keys. So let's do okay. And now you could easily search these. So let's see. So I already did one just to test out. So I chose the option 3, which is to search, and I searched key for 25, and it found variable 25. So let's try value 25, sorry, and then let's try that again. So let's do, I believe I did key 30. Yep, so it found it at right there. And then let's make sure the other one works. So 35, and it found it again. So it actually allows you to search instantly using the hash table order 1, which is very important. And the in order traversal actually works as well. So as you can see, I clicked option 5, and it's fully in order, which is very clean and very useful. So now let's go display, see if that works. Yep, this looks great. So now let's go back and let's talk about cache-friendly AVL trees. So what are cache-friendly AVL trees? So unlike a pointer-based tree, this version stores nodes in a contiguous vector instead of pointers. Children are referenced by indices. So why it's advanced is that the CPU cache lines love contiguous memory. There's fewer cache misses, faster traversal and rotation, and they are great for performance and critical systems. So example use cases of this are in game engines and memory allocations. So let's get into this. So let's insert some values into this. Let's do let's just do one more here. And then, so I inserted those values. So now let's just run it in order traversal, see how that works. And perfect, it's in order. And this shows how the layout actually works. So yeah, so that wraps up my AVL tree project, which showed how these 4 new topics work. So we went through threaded AVL trees, persistent AVL trees, AVL hash hybrid trees, and cache-friendly AVL trees. And each one demonstrates a unique optimization that solves a real-world systems problem, whether it's traversal speed, lookup time, or CPU cache efficiency. All of this is very important and very important to know in data structures. So thank you, and if you enjoyed this demo, feel free to leave a like and subscribe so you could continue learning with me about data structures. And make sure to also look at my previous videos on this. So if you're not familiar with AVL trees, you could look at the basic videos I did. I did another one on in the Linux terminal, which was more just like basic stuff. Not as advanced as this one, and I also did a couple of slideshows to make you guys familiar with how AVL trees work and what they're used for and stuff like that. So yeah, thank you and have a great day.